this lecture, we learn about transport layer. This is chapter 3. This transport layer is being used to send the data from the application layer to the below layer, network layer. And also the data from the network layer to the application layer. This layer is being used. Our goals are described here. To understand the principles behind the transport layer services, main concept to provide this service, multiplexing and demultiplexing, we learn about those concepts. And also we need to understand the concept for the reliable data transfer. And also we need to do some control scheme, that is flow control. And another one, to protect our network from the congestion, we need some mechanism, that is congestion control. In this chapter, we learn about Internet Transport Layer protocols. In terms of the protocol, two protocols are related. As we learned in the previous chapter 2, UDP and TCP. In this UDP, we will send datagram, and that is called connectionless transport. That means without any connection. TCP, that is connection oriented, and also that is reliable transport service. This connection oriented means this is similar to the connection. This connection scheme is being used by the traditional telephone switching technology, and this one is using packet switching technology. Even though this one is not circuit switching technology, it is emulating a connection oriented. That means connection like transport service. Also, there may be some traffic jam in our real express highway. Similarly, in our packing network, there may be some congestion. In that case, we need to provide some congestion control, and that is related to this TCP, and we learn. This chapter 3 is composed of 7 sub-chapters. First one is transport layer services. After that, one of the main concepts provided by this transport layer is multiplexing and the demultiplexing concept. There's this one is described there. And there are two protocols. One is connectionless transport, that is called UDP, user datagram protocol. And another one is transmission control protocol. We learn. This is not using connection. This one is using connection. Thus we will learn those two protocols in this chapter. And to understand better about TCP, because that is providing reliable data transfer service, we need to understand the basic concept and basic principles about that reliable data transfer. And the chapter, in this chapter 3.5, subchapter actually, we learn about connection-oriented transport, TCP. And after that, we learn about principles of congestion control that is provided by this TCP protocol. And more in depth, we learn in this subchapter about the congestion control. Transport services and protocols. Our main purpose to send the data from my side to other side, or to receive from other side to my computer or my smartphone. That is the main purpose, and this transport service is doing some transport related service. And before that, let's look at this one first. Provide logical communication between application processes running on different hosts. Transport layer is providing logical communication. The opposite concept of this logical communication is physical communication. And logically, this one is providing communication link. And transport protocols run in AND systems. For example, this one is AND device. Also, this one is server, but this one is located in the AND side. Thus, that is called end-to-end. And this protocol is end-to-end protocol. Send side. If we are assuming this notebook, here we are sending something, some file, or whatever, that file should be broken into small pieces to send properly. Breaks application messages into segments, that is called segments. In this transport layer, there is small piece, chunk, or packet, that is called segments. Passes to network layer. In the network layer, that is called packet, but in this transport layer, we can differentiate. That small chunk is called segments. And let's assume this server is receiving that. Receive side, this one is reassembling because that is chunked and broken into small pieces. Thus, we need to make it complete file. Thus, that is called reassembling. Thus, this one is reassembles segments into messages, and that will be passed to the application layer here. Vice versa, in reverse way, if this one is sending to my smartphone or my notebook, that will be broken into small pieces. The original large file will be broken into small pieces, and that small chunk, those should be reassembled into one complete message or file, and that will be transferred to the application layer. More than one transport protocol available to applications. Long time ago, around the 1980s, 1990s, there were many protocols introduced in the world, but later we need to simplify, and actually the world in the commercial market, the simplification is done by invisible hand. For example, this is the strongest and powerful standard will be surviving, and we are using that survived protocol, that is called TCP and UDP, about this transport layer protocol. In the internet, we are using that TCP and UDP, even though there have been many different protocols, those are being used. Let's look at this slide. Transport versus network layer. Transport layer, network layer. What's the main difference between them? Network layer is a kind of logical communication between hosts. But transport layer is same logical communication, but between processes, between application program or application processes. And this one is relying on or enhances network layer services. Sometimes in this computer network lecture and in this textbook, some analogous examples are shown for better understanding. Let's look at this household analogy. Let's assume there is Anne's house, and in other side there is another Bill's house, and 12 kids are living there in Anne's house, and those kids are sending letters to corresponding 12 kids in Bill's house. This one is the analogous example. In that case, we can think the host as houses. Thus, these houses can be considered as hosts in our terminology in the computer network. And The process is, in this computer network terminology, that is similar to these kids in this household analogy. And application message in our computer network terminology, in this transport layer, those relate to that letters in this household analogy. And transport protocol here, that is similar to that N and Bill, who is demultiplexing to in-house siblings, brothers and sisters, to distribute the received letter. And network layer protocol can be considered like postal service in our real analog here, analogous example. And I'll explain a little more in detail about this analogous example later. Internet transport layer protocols, let's focus on this here. Among 5 layers, we are focusing on this transport layer protocol here and here. And they are communicating. And that is called the logical end-to-end transport. And this transport layer protocol, this is reliable and in-order delivery. That is a characteristic of this TCP. To provide this reliable and in-order delivery, we need this congestion control. If there is any congestion in the network, also we need to provide this flow control, and also we need to provide this connection setup to proceed to the next communication. This is called connection establishment. This is the characteristic of this TCP. But instead of this, more simplified one is UDP protocol, and this one is providing unreliable and unordered delivery. That is called user datagram protocol. And this one is like no frills extension of best effort internet protocol. Internet protocol, that is network layer protocol, and similar to that, because that is also unreliable and unordered delivery. This one is similar, but this one is transport layer protocol. This one is network layer protocol. Best effort means it is not perfect. The UDP is not perfect, but TCP is 100% perfect. The delivery is guaranteed 100% perfectly. And the service is not available, delay guarantee, that is not possible in both cases. And the bandwidth guarantees, that is not possible in both cases, because initially when this one is being designed and developed at the early of 1980s, around that time, when this one is being standardized, that goal was not considered at all initially. Let's move to the other subchapter. Next one is about multiplexing and demultiplexing. This concept is related to the both UDP and TCP. Thus, this one will be used for explanation for both protocols, UDP and TCP. Here, multiplexing and demultiplexing. Usually, this concept is also used in the hardware digital circuitry. Multiplexing means many different signals are combined into one, aggregated into one. Demultiplexing is in reverse way. opposite concept of this one. Single one, many signals are combined together, then that should be distributed to the proper destination. Then that will be distributed. This concept is related to that, but in our case, this one is being used in transport layer protocol. Think about the mail delivery. Okay, mail is arrived. Let's assume this one is one house as an analog example, household, and received some mails, and that is being distributed to the each kid. Then that is called demultiplexing. When they are sending, let's assume this one is the kids, and they are sending some mail to other friend, to their each friend, and then this transport layer is sending, and this one is dealing with many application processes, or in our analog example, many kids, and this one is providing service for them. And that is the multiplexing, and aggregate together and due to some ID, and this one is sending to the proper destination, and that is the reverse operation. When mail is being received, then this one is distributed to the corresponding application process or corresponding kid. In our example, analog example. Okay, let's follow this one. Okay, multiplexing at sender side, this one, handle data from multiple sockets like this, add transport header here, later used for demultiplexing, that ID, and to differentiate different mail from different kid. And we'll learn a little bit more in detail later. Here we are focusing on the multiplexing concept here. And demultiplexing at receiver use header information to deliver received segments to correct socket. To deliver to the corresponding application process, or in our analog example, to the corresponding kid in Bill's house. Then how demultiplexing works. To differentiate between different mails or differentiate different segments to deliver properly to the application process, or deliver properly to the analog example, in our analog example, to the corresponding kid. How we can differentiate? We need some ID. Here, let's follow this one. Host receives IP datagrams. Each datagram has source IP address and destination IP address. This one is explained about the network layer. We are learning about transport layer above that network layer. Here we cannot see this IP address because that is belonging to the network layer. But we are learning about the transport layer above that network layer. Host each datagram carries one transport layer segment. And each segment has source, destination, port number. Here, in our transport layer, we are dealing with this port number in this transport layer. And network layer, that layer is dealing with this IP address. And this host uses IP addresses in the network layer and the port number in this transport layer protocol. That is combined together, that is called socket number, as we learned in the previous chapter 2. And this socket number will be used to direct segment to appropriate socket, because we can differentiate socket using that socket number. That is composed of address, IP address, and port number. And among them, port number is here in transport layer, and IP address is in the network layer. Okay, let's look at this one. TCP UDP segment format. Our protocol concept will be merged into our protocol format. Thus, we'll focus on that format because that is the finalized and standardized result every day we are using and our program is using. Depending upon that syntax and depending upon that semantics, also depending upon the structure, our program is learning. Okay, here transport layer protocol, we learn in detail about this later, but conceptually and generally, these very primitive port numbers are embedded and included in this segment format. Here, this one is source port number, and we can imagine that this one is 32-bit, thus half of that is 16-bit. We are using 16-bit port number in our real TCP Internet protocol. Destination port number 16-bit. Thus, the maximum number 2 to the power 16 is 65535. Thus, in our last Python program, we could use below and include 65535 any number. If possible, that should be large enough, big enough to avoid any conflict if the other port number that is being used by other program. Thus, we can use in our practice for TCP UDP socket programming. Add header fields here. We look at this one in detail later. And application data, payload. This application data that is, in other words, that is called payload. This terminology is borrowed from traditional telephony area, telephony technology, because telephony technology is wrong technology, and this packet technology is just introduced 1960s. But telephony, that is introduced first time the year of 1876. After that, telephony switching technology and many telephone traditional telephone technologies are introduced after that. This one is holding the data received from application layer. That will be embedded here. Okay, let's look at UDP first, because UDP is simpler one comparing to the TCP, and that is connectionless. Less means without, because UDP is not using connection. This one is about demultiplexing for UDP. Recall, created socket has host local port number. For example, in our previous example, Python example, in the previous chapter 2, Datagram socket will be created in this way. My socket 1 is created like this, and this is the port number. When creating datagram to send into UDP socket, must specify destination IP address and destination port number, as we did already in the Python program, in the socket program in the chapter 2. When host receives UDP segment, that host is checking destination port number in segment and directs that UDP segment to socket into that port number. IP datagrams use the same destination port number, but different source IP addresses and or source port numbers will be directed to same socket at destination. Even though the source IP addresses are different, they are going through the same socket. They are using same socket. In UDP, that is the case in the UDP, but that's different in TCP, we learn. Next slide. But anyhow, we'll focus on the UDP first because, as I mentioned already, that is simpler one. Connectionless, demultiplexing, that is mainly used for UDP. For example, this is the socket number, and that datagram socket, UDP socket, is created here. And here another one. There are two clients, a simplified example here with different port number, and this one is server socket, the others are client socket, we can assume, and they are sending to this server, even though they are different clients, they are using same server socket here. Okay, this one is sending, then the packet, this is called datagram, and that datagram is containing the source port number and destination port number, as we observed in the previous transport layer protocol segment format. Source port number and destination port number. Here, source port number, and this one is destination port number. In the Internet Protocol network layer, this one is holding another IP addresses, but here let's focus on that port number because these port numbers are being used in transport layer protocol, and now we are learning about transport layer protocol. And also the segment from this one to this one. Well, this one can be thought as packet, but the terminology used in this transport layer is generally as a segment. We are calling this packet. This is called segment. This segment format here, the source port number is this one, and the destination port number is this one. Similarly, even though this one is not described here, source port number here and destination port number here, and in reverse way, source port number here and destination port number here. But the main thing to focus on here is, even though they are from different clients, they are using same socket in this server. Next topic is about the connection-oriented demultiplexing. We are learning about demultiplexing. First one is connectionless. That was mainly for UDP. This one is about TCP because this one is using connection. Not exactly same. Thus, this one is called connection-oriented. Connection, that is being used, as I mentioned already, in the traditional telephone switching. That is called connection. But this one is emulating that traditional telephony technology, and that is similar to that connection, and this one is connection oriented using packet technology. TCP socket identified by these 4 tuple. This one can be pronunciated as 4 tuple also in the United States, but in the United Kingdom, 4 tuple. Okay, I'll pronounce as 4 tuple here. Source IP address and the source port number and destination IP address and destination port number. Those 4 tuple can identify with that. Demultiplexing, let's focus on that demultiplexing first. receiver uses all port values, port tuple, to direct segment to appropriate socket. And the server host may support many simultaneous TCP sockets. Because server is providing service for many different kinds of clients, there may be many simultaneous TCP sockets, and each socket that is identified by its own port tuple. Port tuple is here, they are here. Web servers have different sockets for each connecting client. In case of non-persistent HTTP, in that case, this one will have different sockets for each request, but that is so inefficient. Thus, we can assume. Actually, usually we are using persistent HTTP, thus for each connecting client instead of each request. We are using different sockets. Here, this one is example view graph for that. Connection-oriented demultiplexing. As I mentioned, this one is mainly for TCP. Here, each socket, they are differentiated with the port tuple. And here, this one is host IP address A, and this one is host IP address B, and this one is C. And let's look at this one. This source IP address and port number P and 80, and this port number 80, let's assume, and destination IP address is A, here A, B, C, that is IP address, and port number 9, okay, that is not described here. Similarly, like the previous example, 9157, let's assume. Thus, this port tuple that is being used to identify this unique socket. Also, similarly, in reverse way, this socket will be identified with this A and the port number, P and this one. A source IP here and destination IP here. And this connection, that is called the TCP bit pipe, like a single connection between each different socket in the server side, also in the client side. We are using that unique bit pipe, and each socket will be identified with different port tuples like this. They are different. Okay, let's look at other. Let's look at this one. This one is from DC, this one, and let's assume this one is going to this one is 9157 source port number, and destination port number same 80. 80 means web service HTTP application. This one is HTTP, and different HTTP application process is being here used. What thread that may be used. And this one is using some web service, and this one is sent through that socket, and that is holding unique ID that is composed of the port tuple and also different ID. Here, that is socket. We can differentiate these sockets in this way with the port tuple for TCP socket. Here, socket IP port number from DC and different port number, and destination port number same. Even though those are same, here same destination, same source IP, here same. Until here, among the 4 tuples, 3 components are same, but this one is different. Thus, this one is different. Unique. Okay, let's move to the next. 3 segments all destined to IP address B and destination port 80 are demultiplexed to different sockets like this. Also, that different process can be sorted as a single threaded server like this. That is the that is not a major concern in our slide here. Okay, so you can use anyone. Okay, let's move to the next subchapter. This one is about the connectionless UDP transport service, UDP protocol. And the structure of these subchapters are UDP case first, because that is simpler one. And after that, TCP, that will be explained a little more in detail. And even this one, principles of reliable data transfer, that is mainly for TCP. The basic principle concept is described here. After that, our real example about the TCP is explained here, standardized concept. But this one is before that, some general principle. This UDP is just explained in this subchapter. Let's look at this one and let's complete this one first, UDP. User Datagram Protocol. The standardized number is, work number is this one, but you don't need to worry about that, neglect that. No frills, no additional, that means no additional functionalities, bare bones, Internet Transport Protocol. And this one is providing best effort service. Those UDP segments may be lost and delivered out of order to application. That means it is not perfect enough. But TCP is perfect. It is not lost. It is not delivered out of order. TCP in advance. To compare, I am explaining TCP because that is the opposite of this one. Not lost. Delivered in order. That is the TCP's functionality. But UDP is doing best effort service, but best effort means that is not perfect. Connectionless. UDP is connectionless. That means no handshaking, no connection setup between UDP sender and receiver. Each segment handled independently of others. There's one packet, even though those are continuous ones, they may be delivered in different order. Independently, they are going through that internet to arrive in the final destination. UDP is using streaming multimedia application that is loss tolerant and rate sensitive. And I will explain a little more in detail about this later. This one is not being controlled by the strict protocol. There's flexible and a little bit more flexible. There's that is loss tolerant. And this one is being used by DNS and simple network management protocol. Those are application layer protocols. They are using this transport layer protocol, UDP, instead of TCP. And this one is providing reliable. This one may provide reliable data transfer. Actually, it is not providing. It is providing unreliable transfer service, but we can provide reliable transfers we want. If we want to provide reliable data transfer over UDP, then we should use this additional reliability at application layer. And application specific error recovery, we should develop and we should implement that. And also we need to debug. UDP segment header format. This one is 32-bit, that means 4 bytes. That means this one is 2 bytes, that means 16-bit. As we observed already, this one is 16-bit, this one is 16-bit. And length field, this one is using 16-bit. There's whole length, maximum length can be 2 to the power 16. That means 65535. That is the maximum length. That is the byte order unit. 65535 bytes is the maximum length. And this checksum is using 16-bit, 2 byte. And this one is application data. As I mentioned already, this payload means application data. This is the UDP segment format. Please keep in mind, please memorize this one. I may ask in the quiz or midterm exam. Why is there UDP? This is so simple and the functionality is not so powerful. Then why we need UDP? No connection establishment. It is very convenient because connection establishment, to do that, we may need some additional delay time. To eliminate that, we can use UDP and simple. No connection state as send and receiver. If we need a simpler one, then we may use UDP instead of TCP. TCP is complicated and complex one. Small header size, as you observe here, this is very small and simple header field. And the small header size. This one is how much? How long? 8 byte. Each line, this one is 4 byte. This one is 4 byte. That means this header field is using 8 byte. We are using smaller header size comparing to the TCP, and we are not using congestion control, and that means UDP can blast away as fast as desired. Let's look at this UDP checksum. As we observed in the previous segment format, one field among 8 bytes header, the last 2 bytes is about this checksum, and that is UDP checksum. If we are considering UDP, goal is to detect errors. For example, flipped bits, because 1 may be changed to 0 or 0 may be changed to 1. That is called flipped bits in transmitted segment. Sender is treating segment contents, including header fields, a sequence of 16-bit integers to calculate the checksum. Checksum is addition, one's complement summation of segment contents. And the sender puts checksum value into UDP checksum field. After completion of the checksum addition, the checksum, that is the result, and that will be added in the checksum field after that addition. And we look at briefly in the next slide. That will be filled in this UDP checksum field. Similarly, TCP also using this checksum field, and that will be put in there. Receiver side. This one is computing checksum of received segment. And this one is checking. In the receiver side is checking whether there is any error or not. If computed checksum equals checksum field value, no, then error is detected. If they are different, that means error is detected. And those calculated and received checksum, those are same, then that means no error detected. But sometimes that mechanism is not perfect enough. But maybe errors nonetheless. Okay, this one is example how that checksum can be calculated. Let's assume there are so many 16-bit integers. Those are data. Depending upon the data size, there may be more or less. But anyhow, let's assume simply they are added continuously, but we are simply considering two 16-bit integers, and they are added to find out checksum. How they are added here? They are added in this binary format, and finally this one is the carry and wrap around. Also that will be added here. Then the final summation, that result will be like this. And after that, checksum is derived from this after changing 1 to 0, 0 to 1. Reversely, they are being changed. Then that is the final checksum to use, actually to send or to compare. When adding numbers carry out here, from the most MSB, that is called the most significant bit, needs to be added to the result like this. Because this summation, that result is incremented 1 bit more here. After that, that is being reversed. Okay.